Welcome everyone for the first DGRAV seminar of the year. My name is Kent Yagi at University of Virginia, and I'm chairing today's seminar. So it is a pleasure to have Saul Teukolsy and Keefe Mitman as today's speakers. Let me first introduce the speakers. Probably I don't need to introduce Saul, but he's a professor at Cornell University and Caltech, Hans Bede professor at Cornell, and Robinson professor at Caltech. And of course, he's famous for Teukolsky equation, black hole perturbation, but he's also one of the pioneers of numerical relativity. He has this famous, wonderful textbook, Numerical Recipes. He also is an author of white dwarf black holes and neutron stars with Stu Shapiro. And he has received many awards, including Fellow of the APS, Fellow of the AAS, and Dirac Medal of International Center for Theoretical Physics in 2021, and Einstein Prize of APS, again in 2021. For Keefe Mitman, he's a PhD candidate at Caltech under Saul's supervision. He's mainly working, I think, on gravitational wave memory in numerical relativity and also non-linearities in Ringdown, and I believe the latter is what he's going to tell us today. According to his CV, he has already 8 publications, and out of which 5 he's first author, and he has roughly 10 invited talks. So his career record seems pretty impressive. And he has won Best Student Presentation Awards at Pacific Coast Gravity Meeting in 2022. He has also received John Stemple Memorial Prize from Caltech Physics in 2022. Okay, so today, Saul and Keefe will be telling us about nonlinearities in black hole ringdowns. So to remind you the format, Saul will be giving overview presentation for roughly 15 minutes, followed by Keefe for more detailed research talk for 30 minutes. And we'll have Q&A session at the end. So if you have questions, feel free to write it on chat during the talk, or hold on to your question at the very end and raise your virtual hand at the question and answer session. Okay, I think I've introduced enough. So I'll let Saul take the floor.
Okay, thank you, Kent. So just want to make one correction to Kent's introduction. It's not accurate to say that Keefe is a graduate student under my supervision. As you can tell from Keefe's record, he's much more a collaborator than someone that I'm supervising, and you'll see that in the work he's going to present. Okay, so when we look at these marvelous discoveries from the LIGO experiment about merging black holes, what are we actually seeing? What is the physics that's going on? This is a famous sketch from Kip Thorne long before LIGO was constructed. And you can see this merger event is broken up into 3 phases. First, there's the in-spiral. Right, so that's these sort of 2 tornado-like vortice things to represent the spin of the black holes merging. And underneath, there's the gravitational wave signal, the strain that the detector would measure. And you can see it's labeled known. And what that means is that in this part of the waveform, the black holes are far apart, the gravitational field is relatively weak, the speeds are low, so you can use just a correction, the first post-Newtonian correction to Newtonian gravity, and predict the signal. Then the black holes get closer together. There's no small parameters. We have no analytic techniques. We have to resort to supercomputer simulations, and that's this middle part of the waveform. Then the 2 black holes actually merge and settle down to a final black hole. And in that settling down process, they continue to emit some radiation. And as we'll see, this resembles this, if you strike a bell, right? The bell rings with a tone or a series of tones, and then gradually the sound energy carries off the energy from the bell, and you settle down. And this is also labeled known. And the reason is here you can do a different kind of perturbation theory. You start with the exact solution of a Kerr metric, and you make linear perturbations. And in fact, by coincidence, that was the subject of my PhD thesis a little while ago with Kip Thorne. Okay, so we have these tones of the bell, right? The black hole is settling down, and we call them quasi-normal modes, right? Because they're like normal modes of oscillation of an equilibrium structure, except because of the damping, the energy is being drained by the gravitational waves. They not, right? They die out, and that was, we needed another word, and so that we invented, I mean, I didn't invent this, other people invented the name quasi-normal modes. And this has led to a very interesting proposal for testing general relativity called the no-hair theorem. Right? The no-hair theorem says that if you have a stationary black hole, it's described by only two parameters, the mass and the angular momentum, right? The Kerr metric. Theoretically, you could also have charge, but for astrophysical black holes, we don't expect the charge to play an important role. Right? And John Wheeler invented this aphorism, a black hole has no hair. Just to sort of, why would he come up with this particular metaphor? Well, if you look at pictures of John Wheeler, he was completely bald. So this was an early manifestation of bald pride. And the key thing is, it's not necessarily true in alternative theories of gravity. Right? You can see in the figure here, this old illustration of all kinds of ingredients going in to make the gravitational collapse form the black hole, and the final state, everything gets erased. You just need M and J. So this led to this idea that you could test general relativity because these quasi-normal modes are described, they have a frequency and a damping time. So if you could measure two of them, you would measure four numbers, two frequencies, two damping times, and you would check that the mass and the angular momentum could predict all four numbers, right? So you'd have an over-constrained system, you'd have a test. And this idea goes back more than, several decades. And when people started thinking about them seriously around the early 2000s, they estimated that in order to do these tests, you would need things beyond LIGO. LIGO was not even yet detecting signals, but you'd need to go to, Einstein telescope or LISA or something like that, because the signal to noise would be too weak. All right, so I'm not even going to go through this whole slide, but we'll need a few little symbols here. Okay, so if we start with the strain H, it turns out that these perturbations, the analytic description of the Kerr perturbations, is given by this quantity psi4, which you can just think of roughly as two time derivatives of the strain. And the remarkable thing about the Kerr metric is you can separate the variables, right? It's a stationary solution, so the perturbations, you should be able to separate out the time dependence. It's axisymmetric, so you should separate out the phi dependence. But the other two coordinates, which I've called theta and r here, sort of like spherical coordinates, there's no particular reason why those variables separate, but they do if you focus on this quantity, right? So there's an angular function and a radial function. When there's no spin, so the A parameter here is like, you can think of it as the angular momentum. When that's zero, you have the Schwarzschild metric, that's spherically symmetric. This is just a spherical harmonic, right? Technically, for the experts, it's a spin-weighted spherical harmonic. We're not going to get into that. Okay, we don't need that. All right, and then there's a radial function, and you have a nice, like quantum mechanics, a barrier penetration problem, but it's all classical waves. And at late times, the solution, even for the Kerr metric in general, then, is just this outgoing wave. You see the t minus r star. You can think of r star as just the radial coordinate at infinity. For the experts who already know what r star is, right, you don't need to know that. And then you can do a mode decomposition, right? So you decompose the L's and M's, and it turns out for each fixed L and M, there's a radial quantum number, an n, which labels the modes. So you get 3 quantum numbers because it's a 3-dimensional problem. And I use the word quantum numbers, but just by analogy with quantum mechanics, there's no quantum mechanics here. Right? And again, for the experts, right, you observe with YLMs, but the separation is done with these SLMs. These are like spheroidal harmonics. And there's a formula that lets you transform between them. We don't need those details yet. Okay, so we have these modes, right? These sum of overtones. And right, each frequency then is a complex frequency, so it's a real frequency and a damping time. Okay, so this n is called the overtone index because people needed a name for this third index, right? And the no-hair theorem says that the frequencies depend only on the mass and spin of the final black hole. And so the overtone index sorts these modes, these modes by their damping time. So n equal to 0 is the least damped mode, n equal 1, the next least damped, and so on. Now, the choice of the word overtone to label these things was a bad name, because when you tell a physicist you're dealing with overtones, they think that if you increase, the overtone number, you're going to higher frequencies, right? On a piano, right? The overtones of the note you're playing are, octaves above. And also overtones are usually subdominant, right? If you strike the middle C on the piano, the overtones that are excited give that note its color, but they're lower frequency, they're dominated by the pitch of the fundamental mode. And we'll see that that's not always true here. Now, quasi-normal modes have actually been observed. So if you take the first detection by LIGO, this is from their very early paper on testing general relativity. Here's a plot of the quasi-normal frequency versus decay time. And what they did was so IMR stands for in-spiral merger ringdown. So it's the complete signal. So from the early parts of that, or from the complete signal, they have the initial masses and spins. Now, if you assume general relativity is correct, you can plug that in as initial values into a numerical relativity code, which solves the full Einstein equations. And one of the outputs you'll get will be the final mass and spin. And so using the final mass and spin, you can predict the fundamental frequency, right? The dominant mode is the 2-2 mode, and then the fundamental mode was labeled by n equal to 0. And that's the solid black, right? There's some error in the measurements of the initial masses and spins. So this is where you predict to see a quasi-normal mode. Then what they did was they just took the last part of the waveform where everything is exponentially dying away, and they fitted a single damped sinusoid to that and read off the frequency and damping time. Now, if they started at the peak, or here, this 1 milliseconds is sort of very early, 1 millisecond after the peak. The idea is that at the peak, you expect everything to be very nonlinear, so you have to wait for things to die away. And you can see that this green contour doesn't even overlap the true signal. But if they wait 3 milliseconds, that gives you this curve here, and you can see it's still biased away from the centroid, but at least the probability posterior encloses the correct value. If you wait later, then things are less biased, but now you're getting more uncertainty. You're getting buried in the noise. The true signal is decaying away. And so there's this trade-off between waiting long and getting a biased thing. Right, so all kinds of papers appeared on when does ringdown start. Right, so here are the two polarization modes. And then Matt Giesler was a previous graduate student of mine, and he has a calculation which claims that you can use quasi-normal modes even at the peak of the waveform, provided you include not just the fundamental, but a few of the low overtones. Okay, so this is from one of Matt's papers. So what's plotted here is t equal to 0 is starting to do the fit at the peak of the waveform. And the blue curve is just fitting a single sinusoid, right? N equal to 0 here. Then as you add successive sinusoids, you can see what is being plotted here is the mismatch, the agreement. This is not real data, right? That's too noisy. This is being plotted against a computer solution, so a full numerical nonlinear solution, with whose accuracy is way down somewhere over here, right? And you can see the mismatch between the fit and the true numerical solution goes down. And even at the peak here, you can get a very good representation of the signal. So what does this mean? Does this mean that to an external observer, measuring just the strain, a lot of the non-linearity is hidden from view, right? We're just making a linear superposition of overtones and getting a very good representation of the signal. So that would suggest that the non-linearities are small. And the way to understand this is that what's going on is the blue is the fundamental mode, and you can see that at early times, it's not dominant, right? The name overtone is misleading. These rapidly decaying modes are much bigger, right, in amplitude, but they rapidly decay away. And then if you wait up until time 10 in these units of the mass of it's basically the light travel time across the black hole, then this becomes dominant. And for the 1509-14, 10M corresponds in real units to 3 milliseconds. So this would, quote, explain why you had to wait 3 milliseconds before just using the blue curve, you could see a good representation of the signal. Okay, so the possible conclusion is that the early part is dominated by overtones, not non-linearities. Now, needless to say, this was a very controversial result, right? Unexpected. And there's been a lot of work where people have tried to examine whether this is true or not. And that's not the point of today's talk. So I don't want to get bogged down in that discussion. So I'm going to skip over all of this stuff, which is irrelevant to today's talk. But let's just say that it's controversial. We think that there is still good evidence for this. Some other people disagree. That'll get sorted out. But anyway, we redid the LIGO calculation, starting at the peak, but including not just n equal to 0, but 1 overtone. So here's the original thing, blue curve disagreeing with the in-spiral merger ringdown result, but including an overtone, you can see you get a nice, this is nicely inside the contour. And adding another overtone disagrees. This lets you test the note-hair theorem now. It's not a very good test because, I mean, remember this was the first LIGO detection. Signal to noise wasn't very good. but roughly speaking, it agrees to about 20%. Right? You can argue about what that is. There was a paper claiming that this result is not true, that there's no evidence for an overtone in the data. That paper is wrong, okay, despite being published as a PhysRev letter and an editor's pick. Okay, and again, not the subject of today's talk, but anyway. So the summary, right, the introduction to what Keefe has been working on. So as of a few months ago, the ringdown begins at the peak strain. The overtones dominate the early part of the ringdown. The nonlinearities in the ringdown are surprisingly small. I'm going to put seemingly, right? Because there's we're still arguing about this. The overtones enable a first test of the no-hair theorem. We're not going to have to wait until LISA, right? Even the signal to noise of advanced LIGO, right? Maybe even in the next observing run, we can repeat this. And then something I haven't talked about is you can also test the area theorem. And the 1509-14 gives you a 97% test that, in fact, Hawking was right in the area theorem. So that's the background. And what's new? You'll hear that from Keefe. All right, so I'm going to start my share for that.
Thank you very much, Saul, for the very nice introduction. Yeah, let's move to Keefe's presentation. Take it away, Keefe.
Okay, can you see my slides?
Yes, we can.
Great. So first, I'd just like to thank the organizers for inviting me to speak here today, as well as Saul for providing that stimulating history on black hole ringdowns. And so, as Saul said, today, I'm really going to focus on some of the more modern work regarding ringdowns, specifically seeing whether or not these ringdowns are nonlinear. Okay. So essentially what I'll be presenting on today can be summarized in the following 3 items. So first, I'll kind of look into the data that we're going to analyze, specifically looking at the current numerical relativity waveforms and focusing on something unique to these new waveforms, namely this effect known as the gravitational memory effect. Once we've kind of understood what our data looks like, then I'll get into this process of actually analyzing numerical relativity ringdowns, specifically how we fit these waveforms with these solutions to first order black hole perturbation theory, namely these quasi-normal modes or QNMs. And I'll also highlight this importance to fix something known as a BMS frame, which I'll explain in detail, and is something that's actually been overlooked for the past few decades. And then once we know what our data looks like and how to analyze said data, then we can start to answer this question of whether or not there's nonlinearities in that data. Specifically, I'll try to answer this question by examining the gravitational memory effect as a nonlinear effect. And then I'll also highlight some less obvious nonlinearities that we can look for. Okay, but let's look at our data first. And so I should say that this work that I'll be talking about is really based on these 2 papers with many people who have contributed to this work. And there's also a related paper that came out at the same time as ours regarding these nonlinearities. Okay, so for years, this is typically what people think of when they think of a gravitational wave. Here, I'm showing the plus polarization of the strain for a numerical simulation of a binary which resembles that of 1509-14, the first detection made by LIGO. And so as you can see, this is typically what people think of with gravitational waves. There's an in-spiral phase, a merger phase where the strain peaks, and then there's this ring down phase where the strain decays exponentially to 0. But unfortunately, it turns out that this picture, both the numerical relativity waveform and the intuition behind it, is completely wrong. And so what gravitational waves in nature actually look like is the following. So here, the main difference between these 2 waveforms is this effect that I've highlighted in red. And so this effect is known as the gravitational memory effect, and it corresponds to this permanent net change in the average value of the strain. Physically, if you were to observe this effect, what would happen is 2 freely falling observers would experience a permanent net displacement. And so what's particularly interesting about this effect is that it helps us understand this kind of chaotic regime where these binary black holes are merging. And so to really understand this memory effect, it turns out that you have to look to the work of Bondi, Vandenberg, Metzner, and Sachs, who in the 1960s realized that the symmetry group of asymptotic infinity is not the usual Poincare group, but a group with a much more rich structure known as the BMS group. So if you're to try to find the symmetry group of asymptotic infinity where these gravitational waves live, essentially what you want to try to do is you want to take the metric describing asymptotic radiation, and then you find an equivalence class of vector fields which satisfy Killing's equations as you approach future null infinity. And this is really complicated. It's an incredibly complex derivation, but once you go through all of the work, you obtain this vector field, which may seem a little daunting, but is really very similar to what you would expect from the Poincare case. Specifically, this function alpha that appears in front of this retarded time derivative corresponds to space-time translations, and this vector field y corresponds to the usual Poincare boosts and Poincare rotations. But what's specifically interesting about this vector field, and that's new to this BMS case, is that this function alpha here is allowed to be any smooth function on the two-sphere. And so what this means is that you can actually have an infinite number of symmetries associated with this essentially time translation. And these symmetries that are new to the BMS case are what we call super translations. And so this is kind of the complex way of thinking about this. The easier way to think about these additional symmetries and why they exist is through the following. So you can consider a collection of observers surrounding some kind of event, say a black hole ringdown. If they're not all the same distance from this event, as long as they can talk to each other, they could come up with a scheme where they can change their individual watches so that they receive the same information from this event at the same time. But if you then push these observers to asymptotic infinity, then you can freely time translate each of them without changing the underlying physics. That is, because they're causally disconnected, you can change their watches and it's not going to matter. And so these additional symmetries, these super translations, are exactly that. They're simply direction-dependent time translations. But what's particularly interesting about new symmetries is, thanks to Noether's theorem, we know that for each of these symmetries, there should be a corresponding balance law between some kind of charge and some kind of flux, in the same way that a change in your mass is going to be balanced by some kind of energy flux. And so if you identify the charges and fluxes that correspond to these super translation symmetries, the balance laws that you obtain can be expressed in the following. And so these balance laws are a little bit unique in that normally when we think of a balance law, we think of just a charge and a flux. But here you see that there's this extra ingredient showing up on the left-hand side, which is either the real or the imaginary part of this f bar squared sigma quantity. And so this quantity, you should really just think of as the strain. This is just the usual gravitational wave that you see. And so the two balance laws say that the real part of the strain can be written as the real part of this Bondi mass aspect plus an energy flux. And the imaginary part of the strain can be written as this retarded time derivative of the imaginary part of a Lorentz aspect and a Lorentz flux. And so what's particularly interesting about these balance laws from at least a numerical relativity perspective is whenever we extract our numerical relativity waveform, we can use these balance laws to understand where certain contributions to that waveform are coming from. So for example, we could plot a certain spherical harmonic mode of that waveform and see if it's sourced by, say, the Bondi mass aspect or the Lorentz aspect or the energy flux. So to just kind of get warmed up to this idea, let's do that. Well, it turns out that when you look at a gravitational wave emitted by a binary black hole, the dominant harmonic that gravitational wave excites is what we call the 2-2 harmonic. And so what I'm showing here on the horizontal axis, this is just time in our numerical simulation. And on the vertical axis, this is essentially the amplitude of the strain broken up into its different contributions. So in gray, which is hidden behind the black curve, this is the true strain. And in black, we have the mass charge. And in blue, orange, and green, we have the energy flux, the Lorentz charge, and the Lorentz flux, which all happen to be 0. And so this picture shouldn't really come as too much of a surprise, because the 2-2 being the dominant harmonic, we would expect to be sourced by the mass multipole moment. And the mass charge is effectively exactly that. So here, this is really just the usual kind of quadrupole formula. If we look at the next most dominant mode of the strain for this simulation, which is the 2-1 harmonic, we see something similar. And that again, the shear, which is shown in gray and is now behind the orange curve, is almost entirely sourced by this Lorentz charge. And so here what's going on, this 2-1 mode is what we call a magnetic parity mode. And so really what this is showing is that here the strain is being sourced by the current multipole moment, which again isn't too much of a surprise. But where things get interesting is if we start to think about these flux terms. So if you think about the energy that's emitted by one of these binary black hole systems, there's a massive amount of energy emitted over time. So if we're thinking about what an energy flux term will look like, it should change over time, and it should have some permanent net change to it corresponding to this amount of energy being radiated. Furthermore, when we think of the energy, it's typically radiated uniformly in the azimuthal direction. So if we want to find a spherical harmonic mode, which is dominated by this energy flux, we should look for a mode with azimuthal symmetry, namely a mode with m equals 0. And so if we continue down this list, right, we began with 2-1, here we're looking at, or sorry, we began with 2-2, here we're looking at 2-1, and we just continue on to 2-0, what we see is the following. So here I have the strain in gray, I have the mass charge in black, which you can see is responsible for these oscillations near the peak. And in blue, I have this unique contribution from the energy flux. And so this ties back to that picture I showed earlier where we have these new generation of numerical relativity waveforms that experience this permanent net offset. Namely here, we are able to accurately resolve this 2-0 harmonic, which captures this energy flux term and is the first evidence of there being gravitational memory in our numerical simulations. Okay, so this is the data we'll be working with. This is what current numerical relativity simulations produce. But how do we go about analyzing the Ringdown to kind of understand Einstein's theory of relativity? Well, Saul kind of already elaborated on this, but thanks to his very influential work, we know that perturbed black holes emit radiation. And if you work out first order black hole perturbation theory, what you find is that you have these solutions known as quasi-normal modes, or QNMs. And so you can write these QNMs as the following, namely, for any given harmonic of the strain, you have some amplitude, you have some exponential factor where there's a frequency and a damping time, and then you have this factor C, which I'll get into in a moment. So to summarize, right, these numbers that are kind of all over the place, the L and M simply correspond to the angular harmonic, so the spherical harmonic that you're going to be analyzing. This N number is this overtone number that Saul mentioned earlier, which sorts the QNMs based on their damping time. This plus or minus sign, this corresponds to the sign of the frequency, so it can either be positive or negative, and this corresponds to being prograde or retrograde. For the purposes of this talk, we can essentially just ignore this because we'll mainly just be focusing on the dominant contribution, which is the prograde contribution. And then again, these C coefficients are what we call spherical spheroidal mixing coefficients, because when you solve Teukolsky's equation, the natural basis to work in is the spheroidal basis, but with our numerical simulations, we work in a spherical basis. So you need a method to convert between these two bases, and that's exactly what these mixing coefficients are. Okay, now there's something important regarding these QNMs that I haven't mentioned yet. And that's that you have to require that the imaginary part of this frequency is negative for the stability of the solution. Essentially, all that means is that you expect that as your retarded time goes to infinity, you want your QNM solution to decay to 0 to ensure that you have stability. But if you've been paying close attention, this should kind of ring some alarms, because with the numerical waveforms, we know that they don't decay to 0 due to this memory effect, right? We had this picture earlier where the waveform kind of goes up and then it stays up. It doesn't decay to 0. So how on earth can we expect these QNMs to model our numerical waveforms if the numerical waveforms themselves don't decay to 0 while the QNMs do? Well, we can just kind of ignore that question and just try to fit this 2-0 harmonic with our QNMs and see what happens. If we do that, we obtain the following. So here in blue, I have the numerical waveform from this simulation we've been looking at. And in orange, I have the best fit QNM model with 7 overtones. And as you can see, while the QNM model tries to fit the numerical waveform at early times, it's eventually forced to decay to 0 because of this stability requirement. And so what's going on here? Can we just not model waveforms with first order perturbation theory? Do we have to go to higher order? Or is there something else going on? And so fortunately, the answer is the latter. It turns out that these two waveforms are in completely different BMS frames. And so really what that means, it's related to these BMS symmetries that I talked about earlier. But the simple way of thinking about it is when Saul derived these solutions, he worked with a Kerr black hole. But when we run our simulations, the remnant black hole we end up with is not Kerr. It's actually what we call supertranslated Kerr. And it could even be boosted Kerr or rotated Kerr. The idea is that it's the usual Kerr metric, but with some kind of transformation applied to it. And because of that transformation, it makes it so you can no longer apply this QNM model, because the QNM model was derived using a different metric. And so really what we want to do is we want to find the BMS transformations which map our remnant black hole to being that of Kerr. And so the easiest way to do that is to take these charges which correspond to these BMS transformations. So for the super translations, we call the charge the super momentum. For the translations and boosts, we call the charge the center of mass charge. And for the rotations, we have the rotation charge. And so what you want to do is you want to find the super translation, which maps your super momentum to 0, because Kerr black holes have no super momentum. And you want to find the translation and boost, which map your center of mass charge to 0, and the rotation, which aligns your spin with the z-axis. And so if you do this, you go from this picture where your numerical waveform doesn't decay to 0 and you can't model QNMs, to a picture where your numerical waveform does decay to 0 and the QNMs fit it rather well. Okay, and so this is really the idea of what our current generation of numerical waveforms look like and the state-of-the-art techniques for how we can fit them with first-order black hole perturbation theory. And so as Saul said, right, this idea that the black hole ring down being linear is a fairly controversial idea, because you would expect that when these black holes are merging, it's this really chaotic event and there should be a lot of nonlinear effects going on. So at this point, we can really ask ourselves, are black hole ring downs nonlinear? And my answer would be obviously, with a little catch. And so the catch is it depends on where you look. So to really see this, we can again return to these BMS balance laws. So I said earlier, right, the first of these balance laws says that the real part of the strain is equal to this bonding mass aspect plus this energy flux. And so if you write down the equations that define the mass aspect and the energy flux, what you find is that the mass aspect is related to the second Weyl scalar, and the energy flux is purely nonlinear in that it goes as the news squared. So if we were to model the shear or a certain mode of the shear, which has contributions from the energy flux, there's no reason we would expect linear QNMs to fit any contribution from the energy flux, because the energy flux is purely nonlinear. Essentially, this blue curve on the right, again, this is the 2-0 harmonic of the strain. This blue curve, which is the dominant contribution to the strain, there's no reason QNMs should be able to model it, because it goes as the shear squared, and the QNMs should only be able to model the shear. So what can we do here? Well, to see if these ring downs are really nonlinear, what we can do is we can try to fit the data with two different models. One model, which is purely linear, and one model, which is mostly linear, but has some terms we would expect from second order black hole perturbation theory. So to really summarize these models, this is effectively what we'll be doing. So the first model consists of the first three QNMs, the fundamental mode and the first two overtones in the 2-0 harmonic. The second model, which is our test to see if this ring down is nonlinear, contains the fundamental mode and the first overtone, and then this third term, which is what we call a quadratic QNM. And so the idea behind this quadratic QNM is you want to consider two linear QNMs that mix together to yield a quadratic contribution in some kind of spherical harmonic mode. And so for the natural choice for the 2-0 harmonic is you can imagine the 2-2 harmonic mixing with its conjugate to yield some kind of quadratic interaction in the 2-0 mode. Essentially, this is just the memory effect. So it's the QNM generating its own memory effect. And so if you kind of just imagine multiplying these exponentials, what you find is that the frequency of this quadratic interaction just goes as the difference of the fundamental 2-2 mode and its conjugate, which turns out to be purely imaginary. So we would expect this quadratic contribution to the 2-0 mode to be non-oscillatory. Okay, so if we take these two models, which I stress have the same number of free parameters, and we fit them to our numerical data, namely the 2-0 harmonic, what we obtain is the plot on the right. So in black, I have the numerical waveform. In red, I have the linear QNM model. And in blue, I have the quadratic QNM model. And as you can see, just by comparing the waveforms, it's pretty obvious that the blue curve, which corresponds to this quadratic model, better fits the numerical data. Furthermore, if you look at the residual, so the difference between the numerical waveform and either of the two models, what you find is that the quadratic model almost always outperforms the linear model, and the difference between the two is well above the numerical error for this simulation. So this in and of itself is already pretty clear evidence that this ringdown is truly nonlinear, at least in this 2-0 harmonic. Another way to test whether or not this conclusion is true is we can instead do a different type of test. So we can again fit our numerical waveform with some kind of model, but then we can let one of the frequencies run free and see which frequency gives us the best agreement between the numerical waveform and the QNM model. So what we can do is we can simply fit the numerical waveform with the fundamental mode of the 2-0 and the first overtone, and let the frequency of the third term be free, and just find which frequency minimizes the mismatch. And so if we do this, we obtain the following. So here on the horizontal axis, I have the real part of this free frequency. And on the vertical axis, I have the imaginary part of this free frequency. The different contours correspond to the mismatch between the QNM model and the numerical waveform. And the red dot corresponds to the frequency of the second overtone, so something that keeps the model purely linear. And the green cross corresponds to the frequency we would expect from this quadratic interaction. And as you can see, the quadratic frequency lies right on top of the frequency which minimizes the mismatch. So again, this is pretty clear evidence that the 2-0 mode is indeed nonlinear. And really, we knew this to be true because the 2-0 mode exhibits this memory effect, which for years has known to be a nonlinear effect. And so now the natural question is, because we know it's in our numerical data, is there any hope of detecting this in nature? And unfortunately, the answer is no. So here what I'm showing is called the amplitude spectral density curve as a function of frequency. And effectively what this shows is it shows how likely a certain mode of your strain or the strain itself is detectable by a certain detector. So what you want is you want effectively the black curve to be as high above the yellow curve, which is the LIGO noise curve, as possible. But as you can see, the amplitude spectral density curve of the 2-0 mode for a high SNR 1509-14-like event is right below the LIGO noise. And so what this means is that it's going to be really hard to detect this spherical harmonic in a gravitational wave. So the natural question then is, well, is there a different type of nonlinearity in a black hole ringdown that we could try to find in our numerical data that would be more detectable than memory? Fortunately, the answer is yes. So again, we can think, well, the dominant contribution to the waveform during ringdown is this 2-2 harmonic. And so for analyzing the nonlinearity in 2-0, we thought about 2-2 mixing with its conjugate. And so instead, we can just think about 2-2 mixing with itself. And if you think about that type of interaction and you work out kind of the angular dependence, what you find is that you should also expect a nonlinearity from the 2-2 mode in the 4-4 mode. And because the 4-4 mode is much more oscillatory than the 2-0 mode, what ends up happening is that for such an event, like I've shown here, the 4-4 mode is much more detectable. So we can again repeat this process of trying to find a nonlinearity in the 4-4 harmonic. So if we do this, what we obtain is the following. So here I have effectively the same two models as before, where we fit the fundamental mode, the first overtone and the second overtone in the linear model. And in the quadratic model, we have the fundamental, the first overtone, and this quadratic term, which results from the 2-2 mode mixing with itself. And so really what we can focus on is just the bottom panel of the figure on the right, which shows that the quadratic model, the blue curve, is always better than the linear model, the red curve. So again, pretty clear evidence that there's a nonlinearity in the 4-4 harmonic. We can also repeat this process of leaving one of these frequencies free and finding which frequency is preferred by this third term in our model. So this is essentially the same plot as before, but now for the 4-4 harmonic. And again, what you find is while the second overtone is fairly far away from the point which minimizes the mismatch, the quadratic frequency is pretty much right on top of that point. So again, clear evidence that there's a nonlinearity in the 4-4 harmonic. But there's also one last thing you can do, which is because you expect the amplitude of this quadratic mode to scale quadratically with its parent, the 2-2 mode, you can check to see if there really is this quadratic relationship. And so that's what I'm showing here. So each of these columns corresponds to fitting the numerical waveform at a different start time. The horizontal axis is the amplitude of the 2-2 fundamental mode. In the top row, this is the amplitude of the quadratic mode in the 4-4 mode. And in the lower panel, this is the amplitude of the fundamental mode in the 4-4 mode. And so the lower row, this is just to show that for a mode where we don't expect there to be a quadratic relationship, there in fact is no quadratic relationship. Whereas in the top row, there clearly is a quadratic relationship. And so each of these points simply correspond to different simulations. So the circles correspond to simulations that produce a remnant spin of 0.5. The triangles correspond to simulations producing a remnant spin of 0.7. And the different colors correspond to different mass ratios. And so if you take all this data and you fit it with a quadratic function versus a linear function, what you find is that the quadratic function is preferred over the linear function by over an order of magnitude. So again, even more evidence that black hole ringdowns are nonlinear, but it just matters on where you look. Okay, and so that's really the main points that I wanted to provide during this talk today. So to kind of summarize where we're at, we have this next generation of numerical waveforms that contain memory effects. And thanks to these memory effects, it's pretty clear that this ringdown is indeed nonlinear. But with these new waveforms, it also forces us to do something which should have been done a long time ago, which is carefully treat these BMS symmetries to fix them in the proper way and ensure that our remnant black hole is indeed Kerr rather than Kerr in some exotic BMS frame. Then with these new waveforms and this technique of fixing the BMS freedom, what ends up happening is we can clearly see nonlinearities from the 2-2 mode in the 2-0 mode, which corresponds to a memory effect, as well as in the 4-4 mode, which corresponds to a quadratic QNM. And it turns out that there's even more nonlinearities that people have found. This paper I mentioned earlier, which was published the same time as ours, found that there's nonlinearities in the 4-0 harmonic for head-on collisions, as well as the 5-5 harmonic for binaries. And so this really leaves us at an exciting point in strong gravity physics. Namely, we know these nonlinearities exist, but now the question is, can we detect them? Can we explain them from theory, specifically their relationship to their parent modes? And then are there higher order effects? Because we know that if there's quadratic effects, maybe there's cubic, maybe there's quintic, maybe there's nonlinearities from the evolution of the remnant spin. I really think that at this point in time, there's just a lot of questions that need answering. And I'm at least excited about what we're going to learn in the near future. And so with that, I'd just like to say thank you to the audience for their attention, and I'm happy to take any questions that people might have.
Hey, let's thank Saul and Keefe for the great presentation. And now we'll move on to Q&A session. So if you have questions, feel free to raise your virtual hand over Zoom or write your questions on chat. I already see some hands up. So Jeff, would you like to go first?
Yes, thanks for this really exciting talk. So the ringdown is complicated, but I'm a little confused. Is it also the case that the distinction between memory and non-memory is not clear? Is there still a precise distinction between memory and non-memory effects?
So when we think about memory, there's different ways the memory can appear in the strain. So typically people think of memory as having two different contributions, one that comes from this Bondi mass aspect, which is called linear memory, and one that comes from this energy flux, which is called nonlinear memory. And so unfortunately, right, memory in and of itself is just this permanent net change. So it gets a little blurred when you start thinking about the region in between, because the region in between isn't necessarily a memory effect, it's the evolution of the memory. So the memory is really just final value of the strain minus initial value. But we can use this decomposition to kind of understand how the memory grows as a function of time. And that's well understood.
Great. So is that the buildup of the memory monotonic?
It depends on what type of system you look at. So for this system that we showed, the 150914, you can pretty see that it is. But if you look at like a processing system, then you can have the memory kind of oscillating up and down, or if you have eccentric systems, it's kind of like a staircase. So it really depends on the parameters of your in-spiral.
I see. Great. Thank you. Thank you.
Paul?
Yeah, I wonder if you could comment, if you've read it, on a very recent paper which claims that the low frequency noise in LIGO will be low enough that you will see memory in the LIGO sources. Sorry, LISA sources. Okay.
Yeah, so LISA will be a prime candidate for observing memory.
Oh.
Typically, memory falls in the lower frequency band. So for the events that are seen by
Right.
LIGO, it's around 10 hertz. And for LISA, because you're shifting that frequency
No
band.
sound. Okay.
Sorry?
I'm not getting any sound.
Oh,
Okay, now I
Yeah,
do.
can you hear me?
I can hear you, yeah.
Now I got it. Okay, so
Okay.
I'm talking about this recent paper in the
Yeah,
archive.
we heard you, Bob.
What?
We heard your question.
Yeah. So what I was saying is, right, so for the systems that LIGO sees, memory typically lies around 10 hertz.
Right.
And LISA, right, is going to be even farther below. So we really expect LISA to be really susceptible to these memory effects, if not dominated by them. So I think certainly for future generation detectors, we're going to see memory in single events rather than trying to detect it over the culmination of multiple. I haven't seen the paper you're referencing, but I'm, nearly positive we're going to see it in the near future.
Yeah, I give you the archive number if you want, but it was last month. Okay.
Okay. Yeah, maybe throw it in the chat and I'll take a look.
I'll put it in the chat. Okay.
Thank you.
Thanks.
Any other questions for Saul and Keefe? I have one question, Keefe. When you said this 4-4 quadratic mode is detectable, did you mean you've used actual LIGO data, and then found some evidence, or did you just use simulation from numerical relativity and compare that with the noise curve, and so that the signal went above, but you haven't used the actual data yet? Which one is correct?
Yeah, so we haven't performed a formal analysis to see if the 4-4 harmonic or the nonlinearity in 4-4 is detectable. But something that's pretty suggestive is if you look at the top panel of this figure, what you find is that, so here the green curve is the actual contribution to the 4-4 harmonic from this quadratic interaction, and the yellow curve is the contribution from the first overtone. And so what you find is that the contribution from the quadratic term is always larger than the first overtone. And in fact, if you look at earlier times and you compare it to the fundamental, it turns out that the amplitude of this quadratic is actually larger than the fundamental. So what this means is that if you were to detect the 4-4 harmonic for equal mass binary, the loudest signal during the ringdown should be this quadratic interaction. And so that's something that our team, which published this nonlinearities paper, is hoping to look into, is what are the prospects of detecting the 4-4 harmonic? Yeah.
I see. Thanks. Will?
So, Keefe, I have to ask, all of the nonlinearities that you're talking about here, maybe to my amateur eye, I guess, seem like very mild nonlinearities in that they are ringdown modes ultimately sourcing second order ringdown modes. Are you saying you basically don't see any leftover nonlinearities that don't correspond to any modes at all? They come at unusual frequencies in some way or whatever are left over from the merger? or, you know, you mentioned that chaotic space-time that's down close to the holes, it's not, you know, causing a phase of the modes to drag or drift or something in a way that can't just be described as modes sourcing modes.
Yeah, so I mean, it is peculiar, right, that the only nonlinearities we're seeing are really a fraction of the ring down. And so far, the nonlinearities we've seen are ones we kind of expect. So we've seen nonlinearities that are kind of distinct from these QNMs mixing with themselves. So for example, if you have a processing system, when it merges, right, that remnant spin is going to be evolving as a function of time. And so as it evolves, you can see mode mixing between modes, right? So you might see during ring down, you have the frequency of the 2-2 harmonic inside of the 2-0 harmonic, which is, you can think of it as like a time-dependent rotation, right? But I mean, it is strange that it seems we haven't necessarily seen anything that we can explain with kind of what you would naturally expect from these ring downs. I guess the only thing I would say is if you think about modeling, say, the 2-2 harmonic, that plot that Saul showed, where before the peak of the strain, you have really high mismatches. And so I think there's a question of right before that peak, we really don't know what's going on. Are there, you know, nonlinearities that we expect from second order perturbation theory? Or is that just some regime of nonlinearity that we really don't understand? I think it's just that, you know, it's hard to explore that space because we don't know what we're looking for, right? So it's kind of hard to claim it's nonlinear without knowing what the nonlinearity is going to be.
Yeah, right. Okay. Thanks, Keefe.
Mm-hmm.
Sean?
So I'm looking at this plot, and the ring down modes are starting like 20M after the peak. So I'm just wondering, in your analysis where you were looking at the mismatches toward the end, was that going back to the peak and showing no indication of more non-trivial nonlinearity, or was that starting 20M or some other amount of time after the peak?
Mm-hmm. Yeah, so for the nonlinearity I showed in the 2-0 harmonic, that was right at the peak of the strain. For the 4-4 harmonic, this maybe shows it a little bit better. So this top panel is the mismatch between the linear model and the numerical waveform in red, or the quadratic model and the numerical waveform in blue. Right, and so this shows that the maximal difference between these two is right at 20M, which is why I showed the result at 20M. But even if you push this earlier, you know, towards the peak of the strain, the quadratic model is still outperforming the linear model. It's just that for this 4-4 harmonic, for some reason, right, it's still somewhat challenging to get low mismatches at early times. And so this just could be that we didn't include enough overtones. Maybe there's some other kind of nonlinearity that's dominating the signal in that regime. But at least for the 4-4 harmonic, to see the maximal difference, you have to look at 20M. For the 2-0 harmonic, though, you can look right at the peak. So the maximal difference for the 2-0 harmonic is right at the peak. So these nonlinearities, it really depends on what mode you're looking at. Yeah. Does that answer your question?
Yes, thanks. I think it also goes a bit to Will's question.
Yeah.
That is still an open question from those other modes.
Right.
Are there more questions then, or not? Because if there are not any more questions, I'm going to say something about that last question and your response to it.
Okay, but it's almost 4 p.m. It is actually 4 p.m. Eastern, so can you make it very brief and short?
I'll try. Okay. I interpret the nonlinearities and the times that these the decay of the waveforms that you showed to be related to the other, what you call normal modes of the system. And when you start to include those other normal modes in the perturbation theory, then their effect becomes more obvious and creates the nonlinearities that and contributes to the nonlinearity that's inherent in this system. So if you had a complete, I'll call it a complete basis set of the normal modes of the system of space-time in the system that you are working on, then you would see these effects in your theory that you have experienced in your experimental data. That's all I had to say there. Or yes or no, I don't know. You can think about it, and later on we can correspond and I'll tell you about it.
Okay, thanks for the comments. So let's close the seminar today. So let me thank Saul and Keefe again for their wonderful talks.
Thank you.
So the next DGRAV seminar is on March 2nd at 3 p.m. Eastern, same time, by Stephen Taylor and Niham Paul on pulsar timing array physics. So thank you everyone for coming today, and I hope to see you all in 1 month. Okay, bye.